Today, I will introduce a few trends we have seen in the industry and what kind of challenges it represents for us trying to address them. Okay, so very briefly, I will introduce Imagine Optic. We are a privately owned company founded 30 years ago. We are about 60 employees located in different continent of the world, and in that time we have deployed more than 2,000 sensors all over the world in very different industries. So here on the right of the screen you can see some of our customers in these different industries. Our activity is organized we have two main activities. One is wavefront sensing and optical metrology. And I will concentrate on this one, where we use the measurement of aberration to characterize the optical quality of component subsystem. But you can also use these optical aberration in combination with deformable mirrors or corrector elements to compensate for them and improve the quality of system, retrieve resolution, retrieve intensity, and so on, depending on the application. But I won't introduce this part of our activity. So we are measuring the wavefront as a derivative of the phase in transmission through refractive component or in reflection, which gives us access to surface shape, so profiles or 3D surface shape. We can retrieve some parameter such as NTF of imaging system. We can retrieve distortion also of system. We are measuring phase and intensity at the same time, so we can use this combined information to make propagation and calculate PSF of a system in different planes. And we can also use it then to propagate some beams and calculate some n-squared parameters for laser beam testing, for example. So that's a little bit all the parameters we can retrieve from the same measured signal. Based on this technology, again, the Shakartman, which is a very small camera. Here you have an example that's like a webcam. We are currently working on different axes in order to improve the technology and answer to some requests from the optics industry. These axes are improving the resolution. That's a constant work we are performing and innovation. We are working on increasing the dynamic range of our system, together with trying to increasing the testing diameter. So I will show some example of that. And last, we detected a need from manufacturers and collaborators for a testing which is more specific to their application, meaning that's not anymore the sample that has to adapt to the metrology solution, but the metrology solution that has to go closer and match the requirement of the samples and the optics to be, or objects to be tested. So I will a little bit comment on that also. Okay, of course, it will be too easy if we would not have to combine all those characteristics together. So that's kind of an added difficulty. I will skip on the scientific part of that to go directly to the results, as we are a little bit behind the schedule, I think. So that's an example of how we've been working on the algorithm in order to improve resolution of our systems. On the left part of the screen, you have an example of wavefront error map acquired on a window. Each sampling point correspond to a microlens in the case of a Shag-Hartmann system, and this is all these tiny squares you can see. With the same hardware, applying phase retrieval algorithm and somehow better exploiting information contained in the raw signal we measure. Some algorithms have been proposed by the scientific community called LIFT algorithm that allow to improve resolution 16 times. And that's what you see on the right part of the screen. You can recognize the same defects, okay, but it's obvious the increase in sampling points is quite obvious. And that, again, using the same hardware. This is another funny example we use on fairs and our booth as a demo. On the left, you have the transmitted wavefront of this lens. Resolution is 128 by 128 sampling points. And by applying the LIFT algorithm, we are able to increase the resolution up to 500 by 500 sampling points. And again, you can recognize, I don't know, can you see my mouse? Yeah, okay. So you can recognize.
Yeah, we can see.
Okay, the low spatial frequency defects here. But at the same time, you can see this high frequency pattern. This high frequency pattern is the fingerprint of my CEO that we put on purpose on the lens here. And you can see that the increase of resolution is quite tremendous. Okay, so that's taking better advantage of existing systems. Now, once you have that, the advantage is that you can combine it in more complex systems. So this is an instrument that embeds the illumination and works in double pass. So like piezo interferometer, for example. And we use in this system an optical zoom that allows us to maintain this high resolution, 500 by 500 sampling points, whatever the testing diameter is. So from 1.5 inches up to 4 inches or 6 inches. So again, here is an example of flat, large substrate, large and thin substrate. And we have a patent in order to get rid of the back reflection. But again, I won't comment on that today. And here is a wavefront error map that we are able to measure. So having high resolution allows us to filter all the low spatial frequency. So it could be sphere, it could be astigmatism, it could be trefoil or whatever. And observe in this case mid to high spatial frequency pattern, and you will recognize the pattern that correspond to the polishing tool that has been used to produce this flat sample. So that's an advantage of increasing the resolution for our customers. And then what one can ask to himself is, what is the limit? No, I mean, you can build very large refractive based systems. So this is images courtesy of Zygo, of course. This is 24 inches system. You even have 32 inches systems. So that's super cool system. There are drawbacks to this approach. It's super heavy environment to implement them has to be very controlled. It's very difficult to produce such high quality, high accuracy optics. So as a consequence, it's also very expensive, more than very expensive. It's tremendously expensive. So that's a very good approach. In our case, the trend and the development we are making, and Eve before me, I think, mentioned it as also an axis of development for the company, is to limit ourselves to compact, lightweight optical instruments, such as the blue you can see on the screen now, and combine it with position scanning. So in this case, this is in the case of large diameter samples. So the idea is to use motorization and a mount in order to scan the sample and increase the diameter of measurement. And at the same time, you can also use this kind of mounting system to perform some angular scanning. And that's a way to take advantage of the scanning to absorb part of the dynamic range requested by the sample. So if you have a divergent system, so here this is a convex lens to measure, one way to be able to see all the maps coming from the sample is to perform this kind of angular scanning. Okay, so in this case, what you get are small wavefront maps, and then you have to combine them all together to get a global map of your sample. That's the technology of stitching. So here, I cannot show you the instrument we built for our customers. So these are some pictures taken in the lab in order to validate the system, the motorized system in different configuration. You will recognize an hexapod. So an hexapod is super nice system, as it allows to move in all the degrees of freedom and with very good accuracy. Okay, and we have different implementation in order to scan somehow the samples. Second advantage of that is that somehow it allows you to go beyond the trade-off you always have to make between resolution and dynamic range or field of view. Right? So that's kind of an upgrade of your instrument to improve this trade. Okay. And fourth axis of development, I was telling you at the beginning of the presentation that we have to go more custom in order to adapt better our solution to the need and the specification of the component. So this is an example of testing at the wavelengths of design and use of the optics, and not limiting the metrology, for example, to the traditional HINI wavelengths at 632 nanometers. But for example, in this case, as requested by the customer, to test, again, from optics, so these are microlenses, in the green spectrum. Okay, and another also example of customization is combining the instrument with automation and motorization in order to get closer and closer to the production line. So thanks to the robustness of the technology and the fact that is quite proof to or insensitive to vibration, we are trying to get closer to the production line, at line or in line. In one hand, to increase the throughput of the measurement as the component goes directly to the metrology station, but also in another hand to avoid manipulation of the sample. When you have large sample or very expensive sample, because you have a lot of processing on them, taking them from the manufacturing line, bringing them to the optical lab, as close as it is, it's a different room, to perform the measurement and then get back to the production line is a risk for the sample, is a loss of time. So that's a trend also we see trying to bring the instrument online, and I also some example of that. And I think that's my last slide. So thank you very much for your attention.